In section 2, we're going to be talking about properties of parallelograms. So we're going to be looking at relationships between sides and angles and also looking at the diagonals of those parallelograms. Now first of all, we want to remember the definition of a parallelogram. It's just that opposite sides are parallel. Okay, that's the definition. When they say it's a parallelogram, that's what we know. The other things that we're going to find out are theorems that are proven after we know the opposite sides are parallel. Now the first one, when we're talking about opposite sides, we're talking about the ones that are not connected. Same thing with opposite angles. We could be talking about A and C because they're across from each other. We could also be looking at B and D for opposite angles. We can abbreviate parallelogram with this symbol, which will make our writing a lot less. It's a long word. We don't have to write it. So our first theorem is looking at the opposite sides. We should notice that they're the same. So again, here is a parallelogram, and I've constructed this parallelogram by making opposite sides parallel. Taking that figure and removing the sides, notice as I move this around, these two opposite sides are always congruent. So our first theorem then is opposite sides of a parallelogram are congruent. That's the short way of writing it. To do a proof of this, and pretty much any of these parallelogram theorems can be proved like this, we can split this with a diagonal, making two triangles. And these two triangles are actually going to be congruent. All we know for sure is that it's a parallelogram, which means that we have parallel opposite sides. Okay, we can mark that on our picture. And if we're talking about both sides here, parallel sides. So the next thing that we should notice is something about our angles here. We have alternate interior angles between 2 and 3, and also between 4 and 1. And so we have two pairs of congruent angles based on the alternate interior angle theorem. Next, we'll notice that there is a shared side between these two triangles, and so those triangles are congruent. And now we go back to what we were trying to prove. We were looking at the opposite sides here. Notice those are corresponding parts of congruent triangles, as are these. And so by corresponding parts of congruent triangles, or CPCTC, then we know that those parts are congruent. If we know it's a parallelogram, we want to find x. We notice that the opposite sides are congruent, so x equals 12. We can also look at consecutive angles. Consecutive angles would be the angles that are next to each other in a parallelogram. So I can see my opposite angles here. I've got my two red angles here. And if we look at these two angles here, if I add those two angles together, notice that we're going to get 180 degrees no matter where I move that. So our proof for this is really simple. We use same side interior angles, which tells us that since these lines are parallel, then we know that these two angles would be supplementary. We would do the same proof then for the next pair of side angles, and then for the next pair. We could do that for all of our angles here. If we want to find x, we'll notice that these angles that we're given, for one thing, they're not congruent. We can see they're different sizes, and since they're in a parallelogram, they're going to be supplementary. So x plus 56 equals 180, and x equals 124. Now the next theorem is looking at opposite angles, which we've already seen are congruent. So angle B is congruent to angle D, angle A congruent to angle C. Opposite angles of a parallelogram are congruent. And to prove that, the easiest way is just to do it using the last theorem, what we know about consecutive angles. Okay, so A goes with B, and B would go with C. So if I just call this A, B, C, think about it this way. We know that if these are same side interior angles or consecutive angles of a parallelogram, that they're going to add up to 180 degrees. Same thing with B and C for the same reason. And so if I do a little bit of work with that, then I should also notice that A is going to be equal to C. So we can get our angle A congruent to angle C. We can do the same work to get B congruent to D. So for a simple example of this, we're asked to find x. We'll note that it's across from the 56, and so these are congruent. X equals 56. We also know then that the diagonals of a parallelogram, so we're looking at these diagonals, as I move around, notice that the blue one and the purple one are crossing there at point E, and so I've measured the distance from C to E and A to E, and notice that I'm getting the same value no matter where I move this. Now the proof of this, we're going to use congruent triangles. I could choose to do either these two triangles here or these two triangles right here. So I'll just stick with these two. And what we're going to do is prove that these two triangles are congruent, and then we'll know that these parts, which are actually the parts of the diagonals, are going to be congruent to each other. So the two red parts will be congruent, the two green parts will be congruent. We can use that in a problem like this. We're asked to find the values of Km and Ln. Now notice that the parts are labeled. Since they tell us that this is a parallelogram, okay, it's in part of the name, it's a parallelogram, we know that the diagonals bisect each other. That means we can look at the parts. Here I have x on this side, and it's going to match with this y plus 2. I can look at the other diagonal with the y plus 10 and the 2x minus 8, and those are also equal. Since I have x and y mixed in each of these, I'm going to do a substitution here, solve these as simultaneous equations. So substituting in for x, it's going to give me negative y and negative 14, or y equals 14. So we have y, let's go back and find x, which would be this equation. So x will be equal to 14 plus 2, or x equals 16. They also asked for Km and Ln. So we can plug those in, or Ln equals 32. And that gives me 48. Okay, the next theorem is looking at when we have several parallel lines put together. The second thing about this is notice that the parts between these parallel lines are congruent. So basically we have equally spaced parallel lines. No matter how I draw the lines cutting through them, if one of them is cut off in equal segments, then the other part will also be in equal segments. We'll see it in this problem here. They tell us AB equals 2, BC equals 2, CD equals 2. That means each of these parts is congruent, and by our theorem here, we'll also see, since these are equally spaced, that EF has to be the same as FG and the same as GH. So if they give you the value for one of those, in this case 2.25, the same would have to be true for each of those, based on the fact that all three of these are the same. And so if I want to find the distance from E to H, notice that I have that 2.25 times 3, which will give me 6.75.